Thank you, sir. Thank you. So my screen is visible?
Yes, your screen
Yes,
is
sir.
visible.
Absolutely, absolutely.
Okay. Thank you. Thank you. Thank you, sir. Actually, let me, tell, something about sir, because my association with Professor Samarjit Kaur is started from 1996. As rightly sir pointed out, we joined the institute at the same time. He joined as a faculty and I joined as a student. And then onwards, it is still continuing. Out of those 100 research papers, probably 20 research papers we wrote together with Arif, myself, and sir, maybe 15 papers. So this is a great learning curve for me also, and every day I am discussing. People may be knowing, and some of the participants may not be knowing. I am, on regular basis we are doing, joint research with myself and Samarjit Kaur sir and some of our students. Even Arif, Dr. Arif is our student. Or he graduated from NIT Rourkela from in 2018. Okay, and then he is continuing, and there are many common work which we are doing. Thank you, sir, for this introduction. So. As the idea of this webinar is highly demanding as well as relevant in the current context, and I believe whatever I shall discuss today, it will be helpful in one way than the other. Okay, so at any point of time, if you have any query, please ask me. You are free to ask me, or later on also you can ask me through my email. My email address is given here, and I shall be happy to answer your queries, and I shall be happy to discuss further on any one of the research topics that I shall be discussing today. Okay, so this talk is mainly you know will be presented on visual surveillance and how basically machine learning can be used in different types of visual surveillance applications. To start with, I must thank to all my students. I have not given the names of the sir because anyway he's with us. So my students, Dr. Arif, Dr. Santosh Behera, Dr. Santosh KK, then current students Ajay, Sritam. There are some more students. I have taken some of the slides from some professors website. So I must thank them also for the resources. Okay. So let me start the talk. So if you look into visual surveillance perspective, you will find that the one terminology which is very important to understand for us, what is computer vision. So when you talk about computer vision or machine vision, we are basically trying to develop algorithms which will make a computer or a system or a machine, whatever you call it, is intelligent, visually intelligent. It means it will understand that what humans are able to understand by seeing. So when we see the scene, we actually try to understand the scene detect by detecting different types of objects present and how they are interacting. So academically, if you try to define computer vision, it looks like that the science and technology of machines that see. Okay, it is particularly concerned with the theory of building artificial intelligence systems that obtain information from images. Why you need artificial intelligence systems? Because image can carry a hell lot of information which is very difficult to interpret at every level. Image data can take in many forms. It can be in video, it can be in depth sensing images, it can be in multiple camera views, it will be multi-sensors data. Say, let's see these examples. We have natural scenes where cars getting crashed. Then we have a night vision camera, as well as we have you know medical images like CT, MRI, those images. So all are basically you know representations of some facts in different ways, either in visible light camera or in IR cam mode or in some other you know capturing modalities. Okay, now why it is challenging? See, this particular scenario, if you look into it, this is a natural scene. Okay. If you want a computer to understand this natural scene and it should answer the queries, you'll have to understand the difficulties. Why? Why it is difficult? Because the number of queries that can be generated out of this single image can be thousands. Okay, and which question you want to answer? So if you want your computer to understand all those questions, then it's a difficult process. Okay, question can be what kind of scene? It can be where are the cars? It can be how far is the building? I've just given three examples, but it can be thousand such questions which can be asked to a person, and the person possibly depending on its familiarity with the scenario may be able to answer some of them or may not be able to answer some of them. Okay. Now, if you want the computer to answer all these questions, there is a difficulty. You need to ensure that the questions are understood by the computer properly. So for understanding the questions, you need to represent the scene intelligently. How do you represent the scene intelligently? That is very important. Okay, that is basically what computer vision tries to do. Okay. So typically, a computer vision system you will find mainly you know three components. One is the scene itself, and then obviously the sensor. We are talking about the camera and the processing unit of the computer. So in our interaction with nature every day, we also have this. We are also part of this system. Our eyes are camera, our brain is the processor, and the scene itself is there. Okay. So now you'll have to ensure that you have a good quality sensor available, which is possible these days because of the you know availability of sensors in many forms. Okay, we shall be able to get those cameras. But what about the machines to which can understand the signals coming from the camera, which our brain actually does very efficiently and also quickly. That's the reason is that why we are able to do it. That's because it has learned over a time. It's not like that we have learned everything in one day. The learning process is a long process. Starting the day we are born, we start learning, and even every day we are learning. Okay, and believe me or not, this human brain occupies a large portion. I mean, the visual cortex actually occupies a large portion of the human brain. Okay. Now, if you compare the machine's vision and the human vision, it looks like this. On the left side, what we see; on the right side, what a computer sees. Okay. So, the interpretation based on the left side can be different based on different persons. So, whether if you want to have a mapping of the same interpretation on the right side, then the mapping has to be created. Okay. And machines usually see none other than 0 1 or some numbers. That's it. Okay, any number, for example. So from these numbers you'll have to understand what this particular scene talks about. It's really hard. So typical research showed that the visual cortex occupies about 50% of a typical macaw brain. So you can understand that how complex the system is. So in a nutshell, we can say that human brain devoted to vision, that anything else, the amount, okay, that's why it is very complex. And when you want a system that tries to mimic the functionality of human brain, it has to be multidisciplinary. It needs to involve artificial intelligence, machine learning, lots of mathematics, neurobiology, imaging, computer graphics, signal processing. Okay, so there are so many interdisciplinary subjects, and it's really difficult for one person to basically to be an expert in all domains. For example, SAR helps me in understanding the mathematics behind this. I try to do the machine learning and AI part, Somebody from the signal processing, helps me in understanding that how the signals can be represented in better way. Okay, so it is an interdisciplinary, concept. I mean to say that it's not at a single person's business. Okay, but why it matters in real life, that is more interesting here. If you look into it, in modern days, we want everything to be at our fingertips, on our fingertips, and we want to basically experience all the fun of the world just by being inside our drawing room, which is not good. But anyway, that's the nature. People are actually getting involved with such kind of work, and this is more true when a pandemic like situation, today's scenario. Okay, so obviously we need technology to ensure that even if we are disconnected physically, we are not disconnected mentally, or we are not disconnected, informatically. Okay, so it can be used in safety, it can be used in healthcare systems, it can be used in security, gaming, fun, social networking things. Okay, so there are many domains where computer vision, visual surveillance related things can be applied, and we can make our life better in one sense. Okay, it started with early thing like in the optical character recognition. If you go to the study, if you go to the literature, you will find that this sort of work started very early, and people were very much interested to understand that somebody is writing on a paper, and if a computer can understand that. Okay, so that we started with a problem like this. Okay, and later on, it went into a more sophisticated applications like face detection, like these cameras these days, they provide many such applications. Not only face detection, there are several other advanced features also available. Smile shutter, then you can have automatic, like object recognition in a supermarket kind of environment, where you want to minimize the errors during manual counting or something like that. These sort of things are always not there. And also it helps us in serious business. Why? You see, this is one scenario which is very much, I'll say, one of the triggering points for me actually to start looking into computer vision and image processing related things, that how it really helps it. So this Afghan girl, she was identified. I mean to say that her identity was established just by comparing the iris. Okay, that's amazing. I mean to say that it's very difficult for humans to, if only the eyes are given. I mean to say that all the Afghani, faces probably having the similar sort of eyes. You may say that visually looking they are similar. No, it's not like that. If I give you 100 mother, faces, you will be confused. But a computer with minute analysis of the textures inside the iris pattern was able to identify the girl and its parents. Okay, so that's an amazing thing, which actually there are so many fields. This is one of the reasons that why computer vision is a success these days. Okay, object recognition has many applications, starting from smartphone markets to business. There are so many. You name something and you will get it. Okay, it has in sports also, and these days in autonomous vehicles, which I still believe that we may be 50 years far from the day when automatic vehicles will come on our roads. Okay, these are still projects which are being run by various companies like Google, Tesla, Mercedes-Benz, Audi. All they are doing their research to understand that how or to make cars automatic. I know that it's very difficult, and I am also pretty sure that it is not going to come in next 20 years, because there are several complexities involved. But people have started investing their money and time into understanding the real problem. Okay, But where actually it matters these days is this. So this particular slide, I'm more interested on this kind of thing. Why? Because here it's not involving any safety kind of thing, rather it is basically understanding the industrial process. So automating the industrial process is possible with the help of computer vision, rather than automating the self-driving, because that is essentially, self-driving is a risky business. If you want to drive your car on Indian roads, it may work on a road in Alaska, or I mean to the Dakota, where, or sorry, in Arizona, where there are deserts and roads are not populated like Indian roads. It may work for some kilometers, but it is never, definitely not going to work on the roads of Haldia, or on a busy place in India. Rather, where it can work is an industrial setup where there are standard pipelines, and you know that a pipeline starts from here and it ends here, and in the pipeline there are 10 stages. Each and every stage performs exactly one task, and you know that beforehand, and you know that what that task means. So if you know that, it is possible to apply automation with the help of visual surveillance. Okay, that is what basically, that's why I told you that I'm really more interested in this kind of task rather than going into fancy design like automatic cars. And obviously this one, this is why, because this is not harmful, this is assistive technology. So if you can bring the assistive technology in self-driving car, then I'm fine. I do not want to make a self-driving car, rather I want to make a car which is assistive driving, or assisted driving, which has assisted driving. Okay. Similarly, healthcare. So CT images, MRI images, there are different other types of imaging, particularly used for medical, in the medical domain, and all these imaging techniques are good to understand the anatomy of our body, to know different physiological conditions. But sometimes, by our naked eyes, we may miss certain things which a computer can help us to understand. That probably you have missed this part. That's why, this is where I'm also interested, that I feel that computer vision and visual surveillance has much role to play. Okay. Now coming to the other part, that this is what all about, what is I'm talking about computer vision or visual surveillance. Now we need to understand that how to make a machine intelligent. Obviously machine should learn it. Okay. So it deals with developing algorithms that allow computers to learn. Okay. So learn to assign an object or an example to one of the several pre-specified categories. That's basically object recognition. Okay. For example, you take this face. Whether it's a teacup, face, or a phone, obviously it's a face. So how do you ensure that machine also understands this? That is what we are talking about learning. So you'll have to ensure that you have a mathematical model that a machine can, with the help of the mathematical model, the machine can understand that whether a given input image is a face or a teacup or a phone. Applications are many, like face detection. The earlier applications are basically coming from the machine learning algorithms only. Due to the success of the machine learning algorithms, we were able to develop certain applications which are helpful to the humankind. And this is another one example of the same thing. Okay. Now, when you talk about machine learning for visual surveillance, then I will like to apply the machine learning in some certain domains. Those domains, for example, crowd tracking. Let's assume a scenario like this, where this is the work being carried out by one of my PhD scholars, Sritam. He is working on understanding the crowd behavior in densely crowded scenarios. You see on the right side, this is a Puri Rath Yatra image. We have started recording the videos from 2016 onwards and trying to understand how people actually behave into those crowded environment, so that we can possibly develop some prediction algorithms that at certain point of time this crowd is going to be in a disturbed conditions, and there may be some accidents, or there may be some stampede, kind of thing. So we can alert the government or the agencies. Okay, and these scenarios are pretty much common in today's scenario. Okay, in political rallies, in socio political gatherings, in religious events, in marathons. Okay, sports activities. You see that maybe thousands and hundred thousands of people are attending events in a closed space. So how do we basically ensure the safety? So we started looking into it, and we started to apply certain physics-based rules, which try to bring the concept of typical particle physics into understanding the human behavior in dense condition. Obviously, we are not talking about sparse condition; we are talking about dense conditions. Okay, so we have applied Gibbs entropy and kinetic energy to understand, and with a little bit of mathematical formulation, we were able to understand that the entropy and energy are varying depending on the density of the crowd. And if you observe these variables, okay, you shall be able to understand that what kind of crowd it is talking about. For example, in this is basically a very much, what I will say, not dense crowd, it is rather semi-dense crowd, but they are moving in a good rhythm. Okay, so what you understand, that the entropy is slightly higher, and energy is also not that much varying. Oh, energy is a little lower. But when you basically try to understand this with a crowd which is more dynamic in nature, and where there are several the direction is not only into one direction, there may be people who are moving across different directions. This is the Puri Rath Yatra image of 2016. And when we tried to analyze this with the same formulation, we found that the energy is slightly more, and also entropy and energy both are varying more than the other type of movement. So these sort of things can give us preliminary idea that how basically such thing can be modeled using physics based thing. Later on, actually, we are still working on it with a more complex model, with the help of you know Brownian motion, in the concepts of Brownian motion, and with the help of Langevin equation, we actually formulated this thing. This work has been recently published in Expert Systems with Application, where we are able to basically classify certain types of movement, and it was able to segment crowd into those large gatherings. So to understand that what is the dynamics of the crowd, and how basically the dynamics varies over time. Okay, so this is all. I'm not going into the formulations of this one, but this is basically based on the typical Langevin equation force model, which is given here. Basically, which our force model, we have an F inertial force model, which has an external force and drift and confinement and a disturbance. Now, when we calculated these forces, and we were able to segment this, and we got pretty good results as compared to the state of the art methods which are available in the literature. Okay, now this is what I was talking about, basically tracking in a high density crowd. Okay, now tracking is why I am actually focusing more on tracking, because tracking is the preliminary task in many of the surveillance applications. Okay, the next part comes basically object tracking. Okay, here actually we in the last part we were not talking about tracking objects. We were rather tracking the crowd, understanding the crowd behavior. We were not individually tracking each and every person. But in many applications, we want to individually track different persons or objects. So a typical framework looks like this. Typical tracking and application framework. Okay, where we have key points, and we extract from the key points, we apply trajectory extraction, which is nothing but the path of the object which is moving, and also we extract the trajectories and put it into the database. We extract the trajectories and put it into the database, and those database are basically those databases are kept into for the further processing, and then we extract features from the database and use it for understanding the meaning of those things. Okay, based on these trajectories, actually we want to see that which are the regions of the scene are interesting. Okay, and we want to do segmentation of those regions, and then it can be applied for many things like abnormality detection, summarization. Okay, there are several other applications possible. There are several other applications possible. Okay, so that is what it talks about. Now, this part of the work is basically Arif carried out several experiments, and he did excellent research in this. I'll be presenting part of his work here itself. So it's basically, when you talk about tracking, we are talking about the position of the object in temporal domain. So the position means x, y, and t. Temporal domain means t. So position, and we are talking about in 2 dimension. Actually, it should be in 3D, because we do not have 3D information available. So that's why we represent x and y. We do not include z here, because we are dealing with a single camera. Okay, and we do not estimate the position of the object in global coordinate system. Rather, it's an image image coordinate system. So that's why it is x and y. Okay, now a motion trajectory, for example, in a 2D representation, it seems to be like this. Say a person has started from the top left corner on the left side of the image, and it has actually arrived toward the bottom of the image. Now in the middle, the person has actually stayed for some time. Okay, and again it came. But if you look into the trajectory in 2D, you don't get that information actually, that how long this person was waiting there. It was not visible. So when you present it in 3D, what you can get it, that you understand that the person was traveling, and suddenly the person was stationary for some time into a location which is basically given in the red shadow area, where basically the person was staying, and the person was staying for some time, so that you get something value toward the z direction. Okay. But tracking is challenging due to several reasons. First of all, it's a natural environment. Many objects are moving. Okay, so sometimes an object goes behind another object, so it will be occlusion, then scale, then environment noise, camera problem, multi-camera, fast moving object, dense crowded scenario. There are hell lot of constraints available if you want to talk about object tracking. Okay, now I'm not going into those details, but Arif did a good work in basically, when to choosing that which of the tracks is a good one. So he actually, proposed, soft computing based method to understand that which one of these tracks are good to be used for the further processing. Further processing means, I was talking about this particular architecture where the region of interest, we want to extract features, and then we want to understand the region of interest. That means it's a part of segmentation of the scene. So that's why this was needed. So long duration trajectories typically look like this. You have a trajectory, even if it may not be, all trajectories may not be long, because of the problems we have seen here, occlusion, scale, environment noise, tracking can fail. Okay, let's see that this one. So this is a video which I am running. I don't know whether the video is, you are able to see the video or not. I'm playing the video from my side. Okay, you can see that these tracking, things are basically particle. This is short time tracking. It is unable to track these objects for a longer duration. Now, with the algorithm, we were able to track these people for a longer duration, even if the person actually, goes in between several other persons, and we were able to track this person. Why it was possible? That's why, because we intelligently we selected the region or the area of the person in subsequent frames. That's why we were able to track the person efficiently for a longer duration. Okay. Now, if you want to apply the same thing on all objects, it's really difficult. I mean to say that there are hundreds of people moving at the same time. Okay. So it's really difficult. So this video was playing. When I was playing the video, are you able to see the track?
Yes, sir. Yes,
Hello?
sir. Yes, sir.
Yes, sir, it
Okay,
is visible. Yes, sir.
good, good. So, what we understood from our experience, we learned through experience that it is really difficult, even if you are able to track some of these objects. Okay, it is really difficult, to track for longer durations, and sometimes due to environmental conditions, it becomes more difficult. So then we need predictions. That's why, say you see a scenario like this. So this is a scene which is taken at my institute from my School of Electrical Science building. It was a heavily rainy day, and the cars were moving. So let me play this in a video. You will see that the scenario is really not good, and still we are able to track. That's because of the association algorithm was good. So we used some association, soft computing based association techniques, which were pretty good, and we were able to track objects even in difficult scenarios. Okay. So for example, the person was occluded, and then also we were able to track. Okay. And now these are good conditions. Good conditions means weather condition is very good, and we will be able to track it. But the problem is that here also you can see small objects which are appearing due to the movement of the leaves, due to the movement of the other objects, short movements, things were coming. Okay. Like larger objects, longer duration things, we were able to track them, and we were able to track them for longer duration. The ID, for example, this 89 ID, this person, this is our residential area. I took it from my balcony itself, so I was able to track the person for a longer duration, even if the person actually went through different occluded regions. Okay. So that was basically tracking by association. So first frame you tag, then next frame you search for it. That's by association. The next way of doing tracking is basically tracking by detection. So you detect the object in each and every frame, and then try to do associate. There we needed architecture like typical object detection architecture like yellow V3 architecture, where yellow is a very famous architecture which is trained on many objects classes, humans, cars, several other objects. I mean, the daily life, hundreds of objects are being added, and it is pretty accurate these days. If you would like to use a pre-trained yellow model, it will be able to detect 90% cases all the objects which are commonly available in our daily life. Okay. But our observations are also on person detection is something like that. So sometimes it failed. Okay. And sometimes we got good results. Okay. We had certain limitations on the hardware also, because it requires a lot of high power GPU computing things. Okay. After that, when we actually tried to do the detection, yellow based detection and tracking, we were able to get very good accuracy in indoor scenarios. For example, this is my department building, School of Electrical Sciences, ground floor. Okay. So we were able to track people with very highly accurate things. For example, this person was carrying 2 handbags, so we were able to track the person as well as the 2 handbags, and that's because of the associate and the intelligent association of the objects. Say for example, this girl is available, and also there is a phone. So yellow was so good that it was able to tell that this girl was probably talking with a cell phone. Okay, so that's the interesting part. So we actually we set three cameras in ground floor, first floor, and second floor. Because our objective was to understand when the person actually comes from the first floor to the ground floor to first floor to second floor, whether we are able to re-identify the person. That was a different objective, but we were able to do it. Okay, so here also we were able to track the person you know with very good accuracy at different scales. You can see that the persons who are behind them also we were able to track them. Okay, and this is a typical framework. This is not our, this is ICIP 2017 work, where basically they applied a simple online deep tracking SODT, and which were able to detect and track persons very good. We implemented this one also. We found that it is pretty good. Okay, and with SODT we were able to track single person. Okay, very accurately. The person tracking was very accurate, and then we were also able to track multiple persons. See, tracking means we are tracking persons. Also, we'll have to maintain the levels. For example, 15 and 17. These numbers, you know, you see, it actually failed after some time. 15 is continued, but 17 became 20. So that means there were small objects which appeared in between. But after some time, this 20 got stabilized. So we were able to track this person as 20th object. Then the 21st object comes on the left side. So this way we were able to. That is the interesting part. I mean, that you'll have to maintain the level of the object throughout its appearance within the scene. Okay, and these are some more results. Okay, we tried to apply this on outdoor scenarios like this, and we were able to track them. Then like this is a slightly more dense scenario on publicly available data sets. This is another scenario. Then this is all of these are all publicly available data sets. We applied this MOT data sets, and this is another one. Okay, this is another one, outdoor scenarios. So it was able to track these objects nicely. If you see, even if they mix, it was able to maintain the levels. Sometimes it fails, but largely it was able to maintain 3-4 levels for some time. Okay, so then came, because it was not perfect always, then came the next work, which is I think 2018. It was a deep adversarial deep tracking, which was even better. Okay, so I'll not go into the details of that track, but actually this was able to predict in a better sense. Okay, now what we were talking about till now, that was basically supervised tracking. Supervised tracking means these objects were identified, and the object detection was a supervised method. I mean, yellow is a supervised thing. Okay, now what about unsupervised? Okay, you do not know the object, you want to track them. Unsupervised tracking is a ocean actually. Okay, so and it is really challenging. I will not go into the details of this classification techniques, which will be obviously discussed by many other experts in this webinar. Okay, but mainly one domain I have started working with one of my PhD scholars, Dr. Santosh KK, who recently graduated. He started looking into the unsupervised nature of the scene, and then try to understand the with the help of graphical model based systems like display process. We were able to solve the tracking problem to large extent in case of unsupervised. Yes. So what we were able to do it with the help of a modified Dirichlet process mixture model, which is a graphical model, and we were able to track objects. This is literally mathematical. I'm not going to details into the mathematical things here, but this is basically based on the probabilistic Bayesian framework. Okay, and we were able to track the objects very accurately as compared to the state of the art. So for example, the right side we have our proposed model, This is tweak which has been published in IEEE Transactions on Intelligent Transportation Systems, which were the algorithm was able to track these objects very accurately as compared to mean shift and KLT. Now, we have looked into the tracking. Now, if we apply tracking for applications, now let's go for the applications. So this application is an interesting application. We are talking about synopsis generation. Let me tell you why synopsis is important here. This is an interesting application, and one of the reasons that why I like computer vision and visual surveillance to be a game changer in next 15 years or 20 years. That's because of such applications. For example, these days everyone is putting CCTV cameras in across all places except possibly the private rooms. Everywhere you will find the CCTV cameras. Now the question is, who is going to look into these terabytes and petabytes of videos every day being generated? Okay, and how quickly you can identify that which are interesting and which are not interesting. So that's why there is a need to intelligently understand that what is an important part of the video and what is a non-important part of the video. That's called basically synopsis. So the definition is something like that. Given a long duration video or a 24/7 video recordings or maybe 7 days video recording, I want to generate a synopsis video which may be of say 5 minutes or 10 minutes, which will be also in the form of video. It's not an image form. It will be in the form of video, but that will tell me that what are the important events happened during the last 24 hours or last 7 days. That's called visual synopsis. Okay. So one thing can be like trajectory guided synopsis. A person has moved and then came back, but in between that time the person has stayed for a longer time. Okay. But that may not be helpful always. It can give us some clue, but it may not be helpful. There are papers like this is a PAMI paper which came in I think 2015 or 16, which talks about visual synopsis of long duration videos. But there are problems, like when we try to see the synopsis, we can see that in a single frame the same person is appearing 2 times, which is not possible. So look into the right side of the image. You see that at 11:41 that person appeared. At 11:38 the same person actually appeared. So why basically you want to put both the same person on the same frame? That makes the synopsis a little bit confusing. We want to avoid these scenarios. Okay, that's why it is more challenging actually. So Arif actually worked on it, and he actually produced a good framework for a typical summarization and synopsis framework, which starts with endless video or a continuous video. We do background suppression, object detection, object segmentation, and then tracking. Then we create the object database, tube database. Then we group the tubes. We want to group these tubes. Some of these tubes are interesting. Some of these tubes can be grouped into one group, and some other can be grouped based on some other criteria, and then try to generate the synopsis. So basically it's an optimization problem, multi-dimensional optimization problem, where you have spatio-temporally, because tube is nothing but the track. Okay, now not only the track is a position, but when you associate a track with a person, the person's appearance also comes. So that means it will occupy certain space into the frame. So you cannot have hundreds of such persons appearing on the same frame. The image will not support it. You have a limit of the size of the image. Okay, W into H. So whatever you want to accommodate, you'll have to accommodate within that frame. Now the question is, if 100 people appeared during the whole video, you cannot stitch all the people on the same image. It will not make any sense. So that's why you'll have to intelligently paste the images one after another, and you'll have to ensure that the chronology is also not lost. That's why it is very much difficult, and it's an optimization problem. Spatially you have to optimize, as well as temporally. Why temporally optimize? Say for example, in a video I appeared at 10:12 and say Professor Kaur has appeared at 10:13. You cannot actually bring Professor Kaur's video in front of mine, because as per the timing, real timing, I have appeared in the video first and then Sir has appeared. So you'll have to maintain that chronology of the. So that's why it's just spatio-temporal, optimization. Okay. Now, once you, let's assume that you solved this problem, which Arif has solved it up to a certain extent, then you want to generate intelligent queries like this. What intelligent queries? Now you have summarized the video, you have given it to the user or the owner of the, of the video, and the owner can now give a query something like that. I want to see a person wearing a t-shirt color, green color t-shirt, running, moving from gate number X to gate number Y. So only show me that portion. So we applied architecture, typical object, classifier architecture to classify humans, cars, two-wheelers, four-wheelers, maybe, dogs, because we applied on common objects which are available on the roads. Okay. And then we tried to generate the synopsis. So I'll give you one output of this. So this is a 1 hour synopsis. 1 hour synopsis means I have recorded the video for 1 hour. Okay. From my residential balcony. From my residence's balcony. Now that 1 hour video I will show you maybe in 30 seconds. And these numbers around these objects, they tell about when these objects appear, at what time these objects appear. Okay. You see that the entire 1 hour video I have just summarized in maybe 40 seconds. And what is my summary contents? My summary contents during the 1 hour, what are the objects moved? Isn't that an interesting thing? I mean to say that you do not need to look into the entire 1 hour video. You just look into those timings when the objects have appeared. And at the same time, what you want to do, you do not want to degrade the quality of the video, and you do not want to make anything look unreal. That is more important, interesting. What do you mean by unreal? You will understand that this is unreal. This is a paper, that Preach et al. That I was talking about, that paper 2015 Kami paper. They actually generated the synopsis, but you can see that the same car is appearing 2 times. That's not real. So that's not real. It's not real. You see, that same vehicle is appearing multiple times and sometimes disappearing. That's why when we actually developed our algorithm, we actually optimized this spatio-temporally, and our object detection algorithm was far better than the existing algorithm. That's why we got better results. Okay. Some people actually tried to do scale down, which is also unreal. Say for example, scaling down these cars, it doesn't make sense. For example, this traveler, which was bigger in size, to fit many objects on the same image, they actually scaled down, and it made the entire video unrealistic, which we do not want. We do not want unrealistic video. Okay. A paper which talks about spatio-temporal objects in optimization, it gives objects are going out of the road. What I am showing now, these are all state-of-the-art research. The first one which I showed is our work. Okay. The next part, which is more interesting, now I want to see all the objects which moved during that 1 hour, but the type should be car. I mean, so we have trained with car and bus. That's why with the same category. That's why bus is also coming. We did not have separate class for bus. Okay, so it was 80-90% time it was able to generate the videos with good clarity, and we got optimized synopsis length. See, one point, for a 1 hour video, our objective is to minimize the duration of the video, output video. We cannot have a 55-minute video as output for a 1 hour video. That's not synopsis. Rather, we prefer a 2-minute video or 3-minute video of a 1-hour video. Okay, so that's why it is more challenging. Like this was car. Now you will, in the previous video, we have only seen the cars. Now on the same video, when I applied for bikes, it will only show you the two-wheelers which have actually moved during that 1 hour and at what time. Okay, it is saying it will only show you that. Okay. Then pedestrians, it will only show you humans which were moving. It will not show you any other objects which were moving. And it's a video, it's not an image stitching, it's basically video. From here onwards, we have started intelligently generating, decision systems. For example, now I make the query more complex in nature. What is the complex query? I want to see objects moving from green to blue. If you look into it based on our objects and clustering, we were able to identify that there are 3 entry exit points. One is the green region, another is the red region, another is the blue region. Okay. So a query can be something like this. I want to see the objects which are moving from green to blue. So it will only show the objects which are moving from green region to blue. Objects, I have not told what kind of object. So it has shown one two-wheeler, it has shown a person is moving, it will possibly show when a car is moving. Okay. But it will only show those objects which are moving from green region to blue region. Okay. And that is why we call it intelligent synopsis. So you basically give a query, textual query, and intelligently it will produce a synopsis of the long duration video by minimizing this duration as well as optimally placing these objects so that you get whatever you want. Okay. So this is what actually we have achieved for intelligent synopsis. So the next part, which we want to actually do it, which is still ongoing research. That is basically, given a video, I want to generate a textual description of the entire video. I want to generate a textual description of the whole video. That will be much more interesting. I do not want to see the whole video. Rather, it will give me a textual representation of the video. It may say that in the video, I have seen 5 cars which have moved from this location to that location. I have seen 2 humans. They came together and then they went away. Okay, at this time. So this way, we want to generate the text, which will be much more meaningful. If a security agency looks into the textual representation of the video, at the end of the day, it can understand that what kind of events happened at what time, so that that person can actually explicitly go into that location of the video and check it that exactly what happened. So again, I am telling, this is an assistive technology. This is not replacement. What it is trying to do, it is trying to reduce the burden on the humans observation. That is the interesting part of visual surveillance. Okay. So we want to apply the visual surveillance techniques by making the machines intelligent so that it can help us in taking decisions. Okay. For example, something can be like this, which is very difficult. That it may be, if you look into this video, it's like this. Okay. And a good textual description can be, it's Dhoni finishing in his own way. Okay. So which is pretty difficult to generate this kind of what I will say text which this text may be having some link with our emotional understanding of the scene, but that is the final what I will say, that is the final objective of visual surveillance. If you would like to achieve something at that level, we need to apply machine learning techniques and appropriate methodology to do it. Okay. So I think this is what I wanted to discuss with all of you, and I thank you all for being here, and the session is now open for discussions. I would like to get queries, questions on the topics that I have discussed.
Thank you, Devi, for such a wonderful lecture. I'm really very happy with this. So maybe people have many questions. Now it is open for the discussion.
Thank you, sir. Thank you.
Now, all the participants are requested to put your questions directly to either to the chat box, or you can ask directly to the speaker.
Yes. I think they can ask directly. So
Okay,
try to answer.
Professor Paul, please let them unmute so that they can come and unmute themselves and they can talk directly to the speaker.
Okay, they can unmute themselves, no problem.
The other speakers are requested to put your questions directly to the speakers. Unmute yourself and place your question, please.
Okay, sir, I'm Rakesh from Kharagpur. Actually, sir, I have a question that here you have just shown that video to text. So here I have a question that are you using NLP here?
Obviously, I mean to say that NLP in a sense, because when I generate the sentence, its Dhoni finishes in his own way. It has to be grammatically correct. Okay. So when you are talking about a sentence, textual sentence, it must be NLP must be there. Natural language processing has to be there. See, I can say after looking into the video that a batsman is there, and the batsman's name is Dhoni, and Dhoni hits a six, and some people are cheering, like Gary Custon is cheering. Okay. Now these are the clues, visual clues which are available to me. Now, how do we generate a sentence which is something like that? It's Dhoni finishes in his own way. You require a lot of processing. I mean, even if I generate the text that this is Dhoni, this is cricket match, this is possibly a Wankhede Stadium, this is possibly Gary Custon, this is Dhoni is hitting a six. These are all individual event text. Okay, and possibly you understand this is World Cup final match. Still, with all these clues, you'll have to generate this text. It's Dhoni finishes in his own. If you want to generate this way also, I mean, this is an example only. The emotion can be represented in many ways. I'm not saying that the text which is written here, that is the absolute correct text or absolutely the best emotion. Okay, you can have different representations. So obviously, the NLP comes here, and you'll have to apply NLP to understand or to stitch these small textual tags which are generated through the visual surveillance, and then generate a meaningful sentence. NLP is obviously needed.
Okay, sir. For this reason, actually, then you have to store lots of images for Dhoni's or Dhoni hit sixes and
No.
Gary Custon.
That's what I'm saying. So that's why I'm saying we do not need to store. That's why. That's the intelligent part is here. Is the interesting part here is that we are able to detect these objects with the help of machine learning, modules. They will tell that whether it is a Dhoni or not. So those things, I mean, so the YOLO. That's why I gave an example of a YOLO framework. YOLO was able to detect humans. I mean to say that they may not be able to detect Dhoni because the framework is not trained with Dhoni's image. But if you train it with Dhoni's image, then I think Dhoni's images, I think it will be able to detect that it is Dhoni. Okay. Okay. I mean to say, this person currently I am showing, he is Gary Carsten. How do I know that he is Gary Carsten? I have seen Gary Carsten maybe 100 times or maybe 1,000 times through TV interviews. That's why. So when you have given me those 1,000 instances to learn the facial features of the Gary Carsten, then obviously you have to give those many instances to the computer. Then only computer will understand. Na? So there is no question that without giving data we will be able to do it. But what I am trying to say, it's possible. We have images which can be used to train the system.
Okay, sir. Thank you.
Next participants, please, you can unmute yourself and ask.
Hello.
Yes.
Yeah, sir, it's Taranpreet here. Sir, I want to know that which algorithm or technique is best for the detection as well as recognition for the object in a video. So I have used faster RCNN. So is there any other algorithm which is which provide more efficiency
You are talking
as
about
faster
object
RCNN?
detection. You are talking about object detection.
Yeah. Okay.
What kind of object you
Yeah.
are talking about? I mean to say that all objects which are
Actually,
available on the web.
actually, suppose if I want to find an object in videos like camera, like for home surveillance. So suppose if anyone has been come in the video, so I want to detect that the who is that person.
Oh, that
So
means you are
which
talking
technique
about
is
person
good for
identification.
detecting that person?
That means you are talking about
Yeah,
person
yeah,
detection.
yeah,
Person detection. So person detection is
yeah,
basically human
yeah, yeah.
detection. Actually, I have not, because of the time limitation, I did not include this part, which was part of my object classification. If you look into it, that person, this part was actually person re-identification, which talks about the who is the person. Okay,
Yeah, yeah.
who is the person?
That who is the
Now
person or yeah.
yes. So, I mean to say that there are several several methods which are available which can detect the person based on its appearance and based on its walking style. I'll ask Arif. I think Arif has a talk, na? I think tomorrow or somewhere. I don't know when his talk is. He may discuss this part. I
Tomorrow
actually
afternoon. Tomorrow afternoon. Yes.
tomorrow afternoon. Okay. So I'll talk to
Sir,
Arif
No,
today.
actually,
yeah,
Yes.
yeah, sir. If I apply faster RCNN, so is this algorithm sufficient for detecting that things?
See, that's what I'm saying. This the answer
Hello.
to your question is yes or no. Hello. Answer to your question is yes or no. It will
Yeah.
detect depending on what is your training set. Okay. And at what quality you have trained it and what quality you are testing. Okay. I mean to say that if you train the system with a large number of samples of the same person, I think with 90% accuracy it will
Hmm.
be able to detect the person. Okay.
Okay.
Okay, so you can look into our
Okay.
no,
Okay, sir. Okay.
actually,
Thank you, sir.
you can look into our recent paper. Arif,
Yes,
no,
sir.
myself, and Dr. Professor Samajit, we wrote a paper that's on person
very,
re-identification.
actually, Debi, I think
Okay.
his question is, I think, little different. Actually, his query was, actually, maybe there are different kinds of unsupervised learning. So he's wanted to know actually if that faster CNN is better for this, or maybe other method are there, so that which method is basically for suitable
Sir,
for
yeah,
that.
I'm coming. I'm coming. I'm coming.
Yes, yes.
Sir, the answer to this question is, see, faster RCNN, when you are talking about moving objects, okay. So when you have a
Yes.
temporal relation, so you are talking about temporal relations. Obviously, those things will be useful when you want to detect a person walking, okay. But if you want to detect static objects, why you are going for RCNN? Okay, rather you go for a typical CNN based, YOLO frameworks like thing. See, YOLO is a very good object
Okay.
detector.
Okay.
Okay.
Good.
Okay. YOLO. Okay. Yes, sir. Okay, sir. Yeah.
YOLO, but
Thank you, sir.
the problem with YOLO is that it is mainly trained with objects, but not classification. If you want to use YOLO, then you'll have to train YOLO with different types of faces. Okay, face recognition. What you are talking about is possibly a face recognition kind of thing. Face recognition. Okay, so whose face it is? If it is person X, person Y, you need to understand the feature. So for that feature understanding, you do not need RCNN, because RCNN is mainly talking about, you are talking about somebody's walking style. That's why I actually gave a reference to this re-identification work. Okay, your problem nicely suits with the work Arif has done it. You look into our 2020, I think, multimedia tools and applications paper, where he actually did the re-identification of the persons by looking into the person's walking style as well as the person's appearance. There actually we can apply RCNN kind of network, because walking style involves multiple frames, and how the posture changes over frame and the temporal relation of the postures can be better encoded using RCNNs. Okay.
Yes, sir. Okay. Thank you, sir.
Hello, Eshan. Do you have any questions in the chat box?
No, sir. No, sir. I was just searching it out, but I didn't find anything. No questions yet.
Chat box.
Because actually we have allowed
Okay, so
all the participants, if they do have any questions, they can directly ask questions to the answer speaker. So I think no.
we should conclude now.
Okay. Let me check. Okay, no, sir. I think questions are not there. So I think it would be better if you kindly proceed with the vote of thanks to our respected invited speaker, Dr. Debi Prosad Dogra.
Okay, so thank you, Debi Prasad Dogra, for such a wonderful talk. So we are really very happy because in this international webinar, actually we have you with as a speaker of this webinar. So thank you, Dogra.
Thank you, sir.
Maybe so with this, maybe we can conclude. Thank you.